So this lesson is a continuation of the content that we saw in last lesson, where I explained how the periodic table can help you figure out the electron configuration. And so we compared two different types of models of the atom, one that was proposed by Bohr and the other one that's proposed by Schrödinger. And we saw that it's actually Schrödinger's model that scientists and chemists use today. Okay, so we also saw that the periodic table is essentially categorized into different groups which relate to the subshells. So this group of elements here is known as S. Okay, now we also saw that helium is actually part of the S group as well, although it's positioned here because it is a noble gas, so it still has to be with its noble gas friends. Then we looked at this group here, starting from, boron to neon, and all the ones underneath, and we called this the P subshell. Okay, and we looked at the middle section here, and we saw that all of these things here, the transition metals, they have the D subshell, and then we looked at finally the bottom there, which is the F. Okay, and so we also investigated, how we would write out the electron configuration. So if I just maybe remind you, we had a look at fluorine and we had a look at the electron configuration. The Bohr's model of fluorine was 2,7, whereas the Schrödinger's model is more complicated. It's more like 1s2, 2s2, and then 2p5. So you can see that in the second shell there are still 7 electrons if you add these up together, but it's just arranged, the electrons are arranged in different geometric spaces. So the categories for this are more complicated. So in the Schrödinger's model, so we use the subshell method to express this. Okay, so now we're looking at something quite, it's still related to the electron configuration, and we're having a look at something called filling order. Now, I'm just going to show you a diagram down here. Now what this diagram is showing us, okay, so there's, as you can see, a lot of boxes. Now I was discussing a little bit about these boxes before. Chemists are not very artistic people. They don't like drawing three-dimensional things. So instead of doing that, a lot of the time, especially if you study this at university, you'll find that they use boxes to represent the subshells. And you can see, and I did speak about this briefly last lesson, that one box is considered an orbital, and it can contain in it 2 electrons, maximum of 2 electrons. And we did have a look at the idea of, the 2p orbital, 2p subshell, which can contain a maximum of 6 electrons. We saw, if you look back at the P group, okay, so you can see that there's 1, 2, 3, 4, 5, and 6. Okay, so there's 6 electrons that can potentially fill the P subshell. Now, let's go back here. So as you can see, in the P subshell there are 3 orbitals which can each contain 2 electrons, so in total that's going to be 6. Another thing that you might be wondering about is, okay, how come these are sort of like displaced and all over the place? Why is it that the 1s is at the very bottom, then the 2s is a little bit higher, then the 2p is a little bit higher, etc.? Now, back in the Bohr model, we saw, let's say we're trying to fill in sodium, and there's sodium, as you probably can tell from the periodic table, it has 3 electron shells. So I'm going to draw 3 circles around sodium. And so the way that we filled the electrons in is we said, okay, 1, 2 in the first shell, then 1, 2, 3, 4, 5, 6, 7, 8 in the next shell, and then finally 1 electron in the last final shell. Now you can see that there's a specific order of this. I mean, we didn't really go, here's sodium. We did not do this, right? We did not just put the electrons first here, 1, 2 electrons, and then just randomly decided to go 1, 2, and then 1, 2, 3, 4, 5. We did not do this, okay? That's wrong, right? And what you'll find is that as you progress outwards, the way that the electrons fill the shells is that the shells closest to the nucleus are considered the most stable, and electrons will fill them in first. And then the electrons will fill the next shell in. And that shell is at a higher energy. Okay, it's harder to fill in this shell than it is to fill in this shell. And the reason why is basically it's a little bit further away from the nucleus, and so it's a little bit more unstable. Okay, so these boxes, coming back to this diagram, these boxes are actually arranged in order of energy. So as you go up, there's higher energy. Higher energy. And this is the lowest energy. It's also, you can talk about it in terms of stability. So the lowest energy is actually the most stable. Things that are the most stable. So electrons and in general nature tries to do activities from the greatest amount of stability to the least amount of stability. Okay, that's how nature operates. So most unstable or more unstable. So it's very important to understand this concept that in the case of, say, sodium, and we looked at sodium right there, the first 2 electrons will actually occupy the 1s 1s subshell first, and the orbital, because there are 2 electrons right there, then there's only 2 electrons that can fit into this orbital. So 1 electron pointing up, the other one pointing down. Okay. Now in the second shell, that second shell, you can see from the Bohr's model that it's completely full. So actually in the second shell, the spherical is full, so it has 2 electrons there. So 1, 2, then 3, 4, 5, 6, 7, 8. So there's 8 electrons in the second shell. Okay, then we're going to be filling up the third shell. Now we don't fill in, you know, that last electron that's right there, we don't put that here, okay, into the 3D shell, because that's far too high. That's not stable. Okay, we have to occupy the more stable orbitals first. So we're only going to fill in the 3s orbital there. Okay, so with 1 electron pointing up. Now, the way you would write the electron configuration for that, therefore, for sodium would be 1s2, because there are 2 electrons there. Then you would have 2s2, 2p6, because there are a total of 6 electrons here, and then 3s1. That's using the Schrodinger's model. If you wanted to write in the Bohr's model, it would just be 2, 8, and 1. They're a lot easier, but it's just not really used anymore because it's not specific enough. Okay, so the idea to gain from this is that each of the orbitals have a specific energy, and we have to arrange the electrons in terms of this particular energy order. That's very important. That's where this diagram called an electron filling order diagram is obtained, and this is what it looks like. Okay, now before you start getting really freaked out, I may just actually explain to you where this all comes from. I might have to get the periodic table, just try to copy it and paste this somewhere here. Oh, that did not work. Okay, let's try it again. Whoops. Okay. So I will just try to minimize this a little bit, just so we can compare them side to side. It will be a bit small. No. Now, let's have a look at what's going on here. One of the things with the electron order diagram, okay, is it's an essential tool that helps you figure out how electrons are actually ordering each of the subshells. So we already saw that the 1s here is from these two elements there. So S subshell can only contain 2 electrons, and you can see that you can only have a max of 2 electrons in that shell. The next one, I might keep it aqua, hang on, is the second shell, which is also the S. So you can see that that's it there. Okay, so and then actually what we do after that is then we look at the P subshell, and you can see that the second one in the second period is the P subshell, because it has a maximum of 6 electrons that are possible. And then we keep following this down, so you can see that in the third period we have the spherical subshell, so that's where that comes from. Then we have the 3D again, so that's that. And then, interestingly, you may not think that this is still part of 3, but it is. And that's all of these guys here. First row of the transition metals. That's actually the 3D subshell there. Even though it's not in the third period, it's still considered 3D. Okay? And then again, we kind of fill it in with the 4 as well. So that's that. This thing here is the 4s, then we have the 4p again right here, and then we have the 4d, which is this group, well, this period down there, and then 4f, and surprisingly the F subshell is found right here. So that's the F subshell right there. And then you can see that the it keeps going like that. Eventually the F subshell kind of runs out at the 5th energy shell. You can see it's 5F, and then it doesn't appear again because there's no 6F or 7F. Okay. Now, so that's basically how these are written. So if I just explain it again, the way you do have to memorize this electron filling order diagram, but all you have to do is just look at the periodic table and go, okay, in the first period there is an S subshell. In the second period there is an S subshell, so it's 2S and then 2P, and then it's 3S 3p, and then 3d. Usually it doesn't go beyond the fourth one. We will look at the fourth one as well. So 4s, 4p, 4d, and 4f, and so forth. So 5s and 5p, 5d, 5f. So you can see that all the S subshells are aligned underneath one another there nicely, and as is the P, as is the D, as is the F. Okay, so they're just listed underneath one another. Now, the other kind of thing you might be wondering is, okay, what are those diagonal lines? Now, those diagonal lines are very important because they tell you the energetic order in which the electrons are being filled in the electron shells. So first they have to fill in the 1s, then they have to fill in the 2s, and then the 2p 3s. So you can see the filling order. So it's like 1s, then 2s, then 2p, then 3s, then it's 3p 4s, 3d 4p 5s, and so forth. So they're actually just telling you that's how we organize electrons. That's the order in which they go from most stable to most unstable. That's the filling order of them. So let's use this, and maybe we can have a look at how we would write out the electron configuration for a certain element. I actually might choose manganese, perhaps. Is manganese a good choice? Yeah, I'll choose manganese. So manganese, Mn. Alright, now it's right here. Okay, so in terms of using this electron filling diagram, so first, to get to manganese, you have to start from the beginning. You have to fill in the first 1s shell. Okay, so it's 1s, and we already know it's perfectly filled, the 2 electrons that occupy this subshell. Then we need to go to the second one. So using our diagram here, after the 1s subshell comes a 2s. So 2s, 2 electrons, then after 2s comes 2p. And p contains 6 electrons in it, right? When it's completely full. And then we go to the third period. So in the third one, we've got the 3s. So you can see that 3s is after the 2p. We fill in 3s. And because we're not yet at magnesium, we're not yet at manganese, right? So we still keep going. Then we do the 3p. And if you look at your diagram here, 3s follows 3p. So we have to organize the 3p, and 6 electrons fit into the third p subshell. And then we actually have to go to the 4s subshell, which you can see is right here. So we have to go 4s2. And finally we get to the transition metal part, which is then the 3d. And here, because it's not completely full, we'll just count 1, 2, 3, 4, 5. 5 electrons are needed to make manganese. Okay, now one of the things is, although this is in terms of energy, this is how you fill the electron. This is how you write out the, well, this is how the electrons get filled inside the atom. But the way in which you conventionally write this or present your answer, it's kind of like, you know, in maths you wouldn't really leave a negative power, say, in your expression, or you would not put a negative term. You know, you wouldn't write something like negative a plus b. It would be much preferred if you wrote B minus A. So chemistry has these kind of conventions as well, and the idea is that really 4 should not come ahead of 3 because it just doesn't make sense. So we actually flip those two around. When we write it finally, your final answer should be more like 1s2 this is how you would present your final answer, 3d5 and 4s2. So we know that the 4s gets filled in before the d, but we write it like this here. Okay, so that's manganese electron configuration. Okay, now yeah, so we might do one for bromine, and then we might stop there. So I'll just actually make some space because I do need this periodic table. So I'm going to get rid of this as well. So let's have a look at where bromine is first. So you can see bromine's right here. Okay. And so let's write out the electron configuration for it. So Br. Now, yeah, so we need to go through again. These ones will stay similar. So it's 1s2 because we already know it's completely filled. Then it's 2s2, just following the electron configuration order, which comes from the periodic table if you didn't notice that already. Then it's 2p6. Which is this one. Then it's 3s2. We go then to 3p6. And then we follow that by going to the 4s, subshell, so 4s2. And we can see that after the 4s we have the 3d. All 10 electrons are filled in, so we have 3d10. Okay, up to zinc, and then the next after the 3d comes the 4p. So we've got 4p, and we count how many steps to get to bromine. So 1, 2, 3, 4, 5. So we write out 5. Okay. Now once again, there's that technical issue of yes, that's in terms of you know, most stable to most unstable. So in terms of energy, I mean, this is still stable, but it's just in terms of the energy of the electrons, it's getting higher and higher and higher at each shell they're at. The way we conventionally write this is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and then we write 4s2 and 4p5. Okay. Now you may notice that in your chemistry books this might be slightly different. We won't go into why that is. For now, all I would like you to understand is the importance of the electron filling order diagram, how it's related to the periodic table, and why we need to use these diagonal lines to help us work out the electron configuration of an element.